sums. Let's talk about, if they're not dependent, then clearly it would mean knowing the value of one random variable will affect the probability distribution of the other. So, I'm going to talk about conditional distributions. Section 6.5.
How many more homeworks do we have before the final?
How many more homeworks? So next week, 1, 2, I think 3 at most.
When's the last day of class?
Last week of April, okay. So your final exams in the last week of April.
Yeah, the finals on a Friday, right?
Oh,
Wednesday, 24th. So the last class is the Wednesday before that, 17th. Because we won't have class the Monday of finals week, will we?
Yes, we will.
Oh, we will.
Yeah,
Classes
classes
on
on
Tuesday.
Right.
Tuesday study.
classes in the 22nd, so we'll have class, and then our finals the 24th.
Right, yeah, the finals are 24th, so. Keeping 2 more homeworks.
Almost done.
Yeah, almost done. Okay. Alright, so conditional distributions. So let's first of all start with the discrete case.
I got one more, just for clarity, the final will be during normal class hours?
Yeah. So if you had 2 discrete random variables x and y, the conditional probability mass function of x given y equals little y, given that y equals y, is defined as it's x and then line y, and so if you know that y takes the value of y, then this is nothing but the probability that x takes the value of x given that y equals y. And if you recall the definition of conditional probability, this is just the probability that x equals x and y equals y divided by the probability of y equals y. That's just by the definition of conditional probability.
Can you write on black?
Now this is just the joint probability mass function. So your conditional probability mass function for x, given that y takes the value of little y, is let's just go like this. That's the conditional probability mass function of x given that y equals y. So this is the discrete case, and we might as well talk about the continuous case right away. And let's see the conditional. So probability density function of x given that y is little y. Let's denote by this. So you've given information about y, and you now are interested in the density function of x, given that you know what y is. That's just the joint density function of the 2 divided by the density function of y at the point. because this, if you remember how, when we talked about conditional probability, what did it mean to condition on something? It means you take your whole probability space, and now you restrict your attention only to outcomes that ensure this happens. Okay? So your space of outcomes is no longer the whole outcome space, but it's only the space that ensures that what happens. Okay? So you restrict your space. All right. And in this case, so in these cases, you're restricting your space to the to only the outcomes that contain y equals little y, and here y equals little. These are your formulas for calculating conditional probability mass functions and conditional probability density functions. So we'll get examples of this. So if you're interested in the number of successes in a random number of trials. So here's the example. So you first roll a die, and let x equals the number showing on the die. Then toss a coin as many times as the value of x. So you first throw a die, and that tells you, and the number that shows up tells you the number of times you toss a coin. So find the conditional distribution of y given x taking the value little x, and what are the possible values of little x? 1, 2, 3, 4, 5, 6. So x is just the possible outcomes of throwing a die. All right. Now this rolling of the die and each coin toss is. Okay. So we're. So all of you understand how we're doing this experiment, right? We throw a die, we roll a die first, and depending on the outcome, that determines the number of times you toss a coin. And I left out something. Yes, I haven't defined what y is. That's okay. Let y equal number of heads. So y is the number of heads in x coin tosses. So what's the conditional distribution of y given x? All right. So we know that depending on the value of x, that's the number of coin tosses. And then if the number of coin tosses is fixed, what is y distributed as?
Binomial?
Binomial, right? Binomial with little p takes value 1/2, because I said it's a fair coin. And your n corresponds to the value of x. So the probability, so let's write like this, is just the probability that y condition on x equals x. So if I know that the number of coin tosses little x, there's just x choose y, 1/2 to the y, 1/2 to the x minus y, which is just 1/2 to the x. And this is for y equals 0, 1, 2 into x. So, simple. So clearly you need to know the value of x. I mean, depending on the value of x, the distribution of y changes. All right. When I ask you to find the conditional probability mass function, and I don't specify exactly what value this is, supposing I don't say condition on x equals 2, supposing I just say x equals little x, your answer will clearly be a function of x. So the concepts aren't exactly anything new because it's just conditional probability. It's just what are you conditioning on? You're conditioning on the value of one of the random variables. All right. Let me mention a few more things about its functions. So some remarks.
Can you take a set, like say 3 and 2 heads or something, and plug it in? Like,
Yeah, okay.
show me-
Supposing I asked you to find, okay, supposing we want to find, I ask you to find so then this probability mass function is choose y, 1 square, y cumulative value 0, 1, and 2. So what is your conditional distribution? Py condition x.
Does it not have to get to
Is
two
it fair
options?
point?
Yeah, it's a fair. So this would be 2 choose 0, 1/2 square. To choose 1, 1/2 square. I'm just writing this out for each possible value.
And those will all equal, those won't all equal 1, right? That'll equal, like if you sum them?
Yeah. So these, when you sum them for a fixed x, a conditional probability is also a probability,
Right.
right? So add these up.
And they'll equal 1.
Yeah.
Okay.
Because this is just binomial, because y is sort of conditional on x, taking the value little x, is distributed as binomial of x.
Right, I just didn't know if it was gonna be, like the probability is divided over all of x.
Well, by definition, this is why I defined it as divided by this, so that it sums up to 1.
Okay,
Okay?
nice.
Yeah, so remember, your definition of conditional probability, you need to normalize so that you divide it by, so you restricted your probability space to only outcomes that contain y equal to 1. So you have to divide it by this probability so that when you add up all the possible x values, okay, keeping y fixed, it should sum up to 1. So if you add these up, this plus this plus this, that will equal 1. So here for any fixed x, if I condition on x, I can write out each of these values. And this would be 0 x and 1, yeah. X choose 1. X choose X, which is 1. I've just expanded this out. So this is the probability mass function where I condition on X taking the value of X. Okay, what else? Also, if you want to see, does that sum up to X? Sum of over all possible values of this. So plug it into your formula. But this, if I sum over all X values, is nothing but again, that's the reason why I divided by this. If I sum over all possible X values, it does sum up to 1. So this is, I have condition Y equals Y, so that's fixed. So now this is a probability mass function for X, where now Y is fixed. So that is a probability mass function. So maybe I can write it as, you can write it in a comment like this, saying that function of this X is a probability mass function. It's itself a probability mass function. And here, a function in this variable is a probability density function. So you keep Y fixed and it's a function of whatever you plug in here. Okay. Supposing I give you the conditional probabilities, and I give you these probabilities, I can find the joint probabilities by, okay, following. Joint probabilities. Probability that, oh, yeah, so let's use the rule of conditional averaging. So this was something that we talked about when we did conditional probabilities. So if I give you the conditional probabilities, how can I find unconditional probabilities? To find the joint conditional probability, I would just multiply this with this. So that's nothing complicated. But if I wanted to find the unconditional probability just for X, that is, if I just wanted this, how would I find that? So this is X takes the value little x, and Y can take all possible values. Right? That's one way I can decompose X. So X takes the value X, so X takes the value X, and Y takes the value Y1 and or Y2 or Y3, etc. Right? So I can decompose it like this. Now, this I can then write as, from our formula, just a definition of conditional probability. This is going to be the probability that X equals X conditional Y equals Y. So here's a problem where if I want to find this unconditional probability, and I've been given the conditional probabilities and the unconditional probabilities for Y, then it would just be averaging these conditional probabilities for all possible y's.
Averaging?
Yeah, whenever, so here you can think of this, x is fixed, so if you're a function of y, you're summing a function of y weighted with its probability.
Mhm.
Probability of y taking effect. That's just called taking the average of this function.
You're not dividing by anything?
This is a fraction.
Oh.
These are the weights.
Oh.
So when I say average of some function, I don't have to divide by anything, right, if I multiply by a fraction.
Mhm.
And this means I'm averaging g of y.
Mm.
Because I sum up g of y, and but I weight it with this probability that y actually takes the value of y. So that's called this is called the average of g of y.
Oh, because the probability is always like less than 1.
Right, yeah. So when you weight it by its, relative frequency.
Mm.
And in fact, that was my definition of average or expected value. All right.
What's that?
All right, coming back to the definition, all right, we had, I can just rewrite it. We used to call it the multiplication rule. It's just the multiplication rule in terms of random variables. Just rewriting that. It's cross multiply. So this, if you remember from conditional probability, this was just the multiplication rule. And what else do we know? If x and y are independent, then we know that their joint probability is just the product of the individual probabilities. So that means this implies that this conditional probability is the same as the unconditional probability.
Which makes a lot of sense.
Exactly. So we know that, I mean, even when I say the word they should be independent, it would mean that conditioning does not change the probability.
Mhm.
So it's the same as the unconditional one. And that's because we defined independence by this, the joint probability is just the product of the unconditioned probabilities. But by our definition of conditional probabilities, our joint probability is the product of the conditioned one times this unconditioned one. And of course, there's another way I could write it. I could, if I look at the probability that x takes the value x and y takes the value little y, I can think of it as, let's look at the probability that y takes the value little y, condition on x, and then multiply it with the probability that x takes the value. This is again this multiplication rule that we had in conditional probability. So remember, when we define conditional probabilities, we could write it as probability of A, I can condition on B, and then weight it with probability of B, or I can look at the probability of B conditioned on A, and multiply the probability of A. You can choose which one you want to condition on. So whatever you condition on, you've got to multiply it with the probability of that. And the way you think about it is, you look at the probability of A and B happening is, A happens, given that B has happened, and you can think of it as B happens with this probability, and knowing that B happens, A happens with this probability. So this is just that rule that I'm using out here. So everything that I'm writing down here, there's no reason to be confused because it's basically just everything that you studied under notation is slightly different. Notation is, if it's the distribution of x conditioning on y, I write x bar y. That's problem with density functions. One example. Call this example uniform on a triangle. Suppose that a point xy is chosen at random
Professor,
yeah.
what does that say uniform on what?
Oh, a triangle.
Oh, no.
Is chosen, let me say, uniformly at random. From a triangle. And we did look at this example of the joint distribution, a uniform distribution over a triangular region. I think that was one of the examples we did when I introduced joint distribution. Yes. Find probability that y is greater than 1 conditioned on x taking the value of x. Alright, so I'm interested in the probability of distribution of y, and in the region, the probability that y is greater than 1 conditioned on x being fixed at a certain value. So to find this probability, this is just, as I said, conditional density functions are also just density functions themselves. So this would just be, I'm interested in this area. I mean, I integrate over this region. I look at the conditional density function, and I integrate over the region y greater than 1. So that's how you find probabilities of it. So with in the continuous case, to find probabilities, you have to integrate the density function over the region of interest. So our region of interest is when y is greater than 1, so I integrate y going from 1 to infinity. And what do I integrate? I integrate the density function of y conditional on x equals to x. So your problem breaks down into the following steps. So step 1, first find your conditional density function. Step 2 would be integrate to get the probability you're interested in. Alright, so step 1. How do we find this? This by definition is just the joint density function divided by conditioning on x. That's a definition of a conditional probability. I'm conditioning on x taking the value little x, so I divide that by that density function. Alright, so first of all, what are these two density functions? X and Y are uniformly distributed over this triangle. So if you don't remember doing this example in class, we can quickly go over it. So let's first determine what is the joint density function for X and Y. In this example, I've told you that it's uniformly distributed over a triangle, x greater than 0, y greater than 0, and x plus y less than or equal to 2. X plus y less than or equal to 2 is y less than or equal to 2 minus x. So let's draw the line 2 minus x. Line is sloping downwards. When x is 0, y is 2. When y is 0, x is 2. So this is your line x plus y equal to 2. Maybe I should write it as y equals 2 minus x. And I tell you that we are uniformly distributed over this triangle. If you're uniformly distributed over the triangle, this density function is constant over the triangle. The constant has to be the area of this triangle. What is the area of this triangle? Your area is 1/2 base times height. Base is of length 2, height is of length 2. So it's just 2. So you just have 1 over the area. 1 over area in this region. If you're uniformly distributed over this, as in the case if you're uniformly distributed over a line, the density function is 1 over the length of the line over this line and 0 elsewhere. So this is the density function for uniformly distributed, uniform distribution over time. Alright. So we have the joint density. How do we get this? We have to integrate.
What's wrong with that eraser?
Oh, yeah, this eraser is no good. This is sort of redistributing. Okay, so we have our joint density function, and
One second. Okay.
Yeah.
The area is 1/2 base times the height, right?
Right.
And so that becomes the distribution function, right?
No, I mean density function.
Yeah, that's right.
It has to be 1 over the area.
1 over the area.
Right,
That's
because-
what
And why is that? So that when I integrate this density function, I get 1.
okay.
If it's 1 over the area, then a constant, if I integrate it over that region, it just gives me the area. So if I have 1 over area times the area, that will give me 1.
Okay.
So remember, it always has to be 1 over the area. Okay, so find fx of x. By definition, that is just the integral over all y's of your joint density function. So you keep x fixed and you integrate over y. So if I have x fixed, and I'm integrating over y, where's your y non-zero? I mean, where's your density function non-zero? So you would put in the non-zero density function 1/2 only if y was between 0 and this point. So what is this point? This is the point 2 minus x. Outside of that, it's so it's 1/2 y, so 2 minus x, it's 2 minus x. 2. All right, so let's plug this back into our formula here. We have our conditional density function is now this joint density function 1/2, and first of all, we can condition on really here your x can only take values between 0 and 2. There's something that you mentioned earlier, but you cannot condition on something that has 0 probability. So we're only conditioning on events that have positive probability. And so for that, x has to be between 0 and 2. 1/2, and you divide by 2 minus x. 2. So you get 1 over 2 minus x. And your y can only take values. So your x plus y has to be less than or equal to 2. So y is less than or equal to 2 minus x. So when y is between 0 and 2 minus x, your conditional density function is 1 over 2 minus x. In other words, it is 0. So that's your conditional density function. And now for the last part, so I said the first thing you need to find was the conditional density function, and then you integrate. So now when you integrate, what do you get? So the probability that y is greater than 1, conditional on x equals x, you're just integrating 1 to infinity, your density function, conditional density function. Alright, so this density function you can integrate from 1, okay, so you're going to have two cases here. Alright. Just by intuition, what is your conditional density function saying? We just calculated the conditional density function, and we got it to be 1 over 2 minus x. Alright, so that means if I condition on x being little x, the distribution of y is 1 over 2 minus x. So if x is fixed, 1 over 2 minus x is a fixed number. It doesn't depend on y, right? So that means this has constant density function over that interval. So if I condition on x, how is y distributed? Y again has a uniform distribution. Because if I fix x here, and this sort of intuitively makes sense. Initially it was uniformly distributed. If I know that my x value is here, then my y is just uniformly distributed over this interval. That makes sense, right? And that's exactly what it says. What is the length of this interval? This is the line y equals 2 minus at x. This point is 2 minus x. So y is uniformly distributed over the interval 2 minus x, and then it's 0 here, 0 there. So you see that y is uniformly distributed over that interval. Now, if I'm interested in finding the probability that y is greater than 1, this conditional probability that y is greater than 1, let's draw this line, this graph again. At the point x equals 1, if I condition on x that x was the value 1, here is 1, 1. Supposing I condition on x taking this value, then the probability that, then I know y is uniformly distributed over this line, right? And what's the probability that y is greater than 1? Say this is 1. If it's uniformly distributed, it's this length divided by this length. So it's the probability of lying out here. If I condition on x takes this value, what's the probability that y takes the value 1? Y, yeah, it will never be above 1. So we now have two cases. So case, if in this case, the probability that y greater than 1, condition on x equals x, is going to be integral from 1 to 2 minus x. Because it's just this density function. So I'd integrate this thing and it would be, what would I get? I'd get 2 minus x minus 1 over 2 minus x. It would be 1 minus x over 2 minus x. Does this make sense? Yes, this is length 1. This is length 1 minus x. So yeah, then we get 2 minus x. So the probability of lying out here is this, the ratio of this length to this whole length. So 1 minus x over 2 minus x, which is exactly what we get. And then you don't have to do a calculation for the case if 1 less than equal to x less than equal to 2. Because when x is greater than 1, then y can only take values to some value less than 1. So then the probability of y being greater than 1 conditionally x equals x is 0. Okay, so this example has some important things in it. One of them is if x and y are both jointly uniformly distributed in a region, if I condition on x, then y is again uniformly distributed, just restricted to that line. Similarly, if I had condition on y, then x would be uniformly distributed over a line out here. So these are important ideas. But apart from that, it is just using formulas. So if you had to find a conditional probability, you're conditioning on the value of one of the random variables, the first thing you need to do is find your conditional probability density function. That's step one. For that, you use your formulas, and then you take it from that and do some calculus and get your formulas, right? And you plug into your formulas, you have your conditional probability density function, and then to find this probability, you need to integrate over the relevant region. So the only things that you need to keep in mind is step one, what do you do? That is find the conditional density function, and then you will know what to do after that. So if you keep in mind that these are the two main steps, the rest is just applying formula and doing calculus. Okay, there's some more remarks about conditional density functions. So if in our definition of cross multiply, I basically get that the joint density function is just the conditional density function times the density function. And that's what, because by definition this was this divided by that. So since we know this relation, this again is like the multiplication rule in continuous time. If I want to find fx of x, I know that that is just the integral of, so this is just all your formulas, you're just like using it again and again. You take your joint density, integrate out dy. So if I apply to this formula, it means I
Integrals from negative infinity to what?
plus infinity.
Right.
Just integrate out over all possible y. Your density function might be 0 in some regions, so when you actually plug in your density function, you will have to adjust these limits of integration. This is just using that formula. So if you don't have your joint density function, if you're given the conditional density function and the density function for y, if you want to find the density function for x, basically this is your, you can either use this formula or you can realize that this equals this, and this is your formula for getting the density function for x and then applying this out here. Then looking at this again, if x and y are independent, by definition of independence, it means their joint density function is just the product of their individual density functions. But by this result, I know that the joint density function is this conditional density function times this density function. Therefore, the unconditioned and the conditional density functions are the same. So when there's independence, your density function does not change when you conditional values of y. So we talked about conditional density functions. We want to conditional expectations. So I'm skipping ahead right now to section 7.5. So doing conditional density functions, we talk about conditional expectations. And I'll come back to some of the topics in chapter 6 later. So conditional expectation. Make a note of the two formulas that you need to know for conditional distributions. In the discrete case, the conditional probability mass function, conditional y equals y, is just the joint probability mass function divided by probability y equals 1. the conditional density function of x given that y equals y is just the joint density function. You need to add this to your list of formulas. So, conditional expectations is probably exactly what you think it should be. It's just expectations, but now we're conditioning on one of the random variables. So the conditional expectation of x given that y takes the value as y of y such and this is something I didn't mention when I defined conditional probabilities. You can only conditional on events that have positive probability. Because by definition, if it didn't have positive probability, you would divide them by 0. So this is the conditional expectation of x given y equals y. It is just the expectation of x, and you weight it not with the probability mass function of x, but with the conditional probability mass function of x. So that's all. And so write down the definition for conditional expectation with a discrete case. Continuous case is the same. The conditional expectation of x given that y equals y is value just the integral negative infinity to plus infinity So, if you recall this definition of expectation without conditioning, it was just, right? And the only difference is now I condition y equals little y. Now, expectation of a random variable x is just a number, right? It gives you its average value of that distribution. So, this is just a number. What would this be? Would it be a number, or remember, I'm conditioning on y. So it'll actually just be a function of y, little y. And here too, it'll be a function of little y. So unconditional expectations is just a number. Here, depending on what you've conditioned y to be equal to, it'll be a function of that little y. Well, you definitely know you're wrong if you take the expectation, you get an answer which involves x. That you know that you've written something wrong. So if you've conditioned y equals little y, your conditional expectation will just be a function of little y. Okay, let's based on this. Mass function is easier. Suppose the joint probability density function of x and y is this, I think you can compute on your own, so I'll give you a couple of minutes to do that. All you're doing is applying this formula. So you first write down that formula, and then you realize that you need to find the conditional density function. So first calculate the conditional density function. For that you need the joint density function, you've been given that, but you also need the density function for y. So first compute the density function for y, which means you integrate out your x from this. So first step, find the density function for y, then use this formula, find the conditional density function for x, and then use your formula for expectation.
Let's see. That like f of x comma y.
Yeah.
Is it
So
wrong
try-
to have a little like xy subscript there?
Yeah, but I mean, I've already told you that this is the joint density function, so this is.
Oh, thanks.
So I may not write this subscript, but I mean, I write this subscript so that it's clear it's the joint density function of x and y, but here I've stated that it is joint density function of x and y.
I see. So when you say integrate out the x, you mean like integrate with respect to x?
Yeah.
That
When
makes
you
sense.
integrate out the x, it means you don't have x in the picture anymore. That's the definition of expectation with conditional density functions. We now need to find this. So that's first find. This is this density function function is given by this, nice rectangular region, so it's nice. So, I can just integrate from 0 to infinity, and it's this function. So integrating with respect to x, all y terms are considered constants. This constant. This is e to the negative constant times x, so it's e to the negative y divided by the constant. So evaluate this at infinity, when x is infinity. Infinity, e to the negative infinity, that approaching 0, and then minus e to the negative y, negative 1 y, and 0. Negative, negative, that cancels, y and y cancel, you get e to the negative.
Why didn't you have to multiply by x? Like,
I'm
over here,
integrating-
you said it was x times x to the 1?
I'm defining density function.
Oh, okay, sorry.
So this density function of y, I take a look at the joint density and I integrate out to x. When we finally calculate the expectation, we calculate x.